Hello everyone, this is Dr. Shaik Ruksana Begam, working as Assistant Professor in Electrical and Electronics Engineering Department from Institute of Aeronautical Engineering, Hyderabad. Today I am here to deliver a lecture on example problems on equivalent resistance. In the previous lecture, we have discussed about what is Kirchhoff law and what are the types of Kirchhoff laws. So Kirchhoff laws are basically of two types. One is of Kirchhoff current law and Kirchhoff voltage law. If you want to learn more about the Kirchhoff laws, you have to visit the previous video. So today's topic will be on equivalent resistance calculations. In the previous lecture, I have discussed about the basics of how to calculate the equivalent resistances when they are connected in series, parallel and series parallel. Basically, why we need to calculate the resistance means in the upcoming lectures we'll be having to solve about the complex problems which will be having more resistances. So to reduce this type of resistances, we'll be using equivalent resistance calculations. So the purpose of equivalent resistance calculation is to simplify the complex electrical circuits and to analyze their behavior more easily. So basically these equivalent resistance calculations will be of three types. One will be series connection and parallel connection, and the third one will be combination of series and parallel. So in this lecture we'll be knowing how to calculate when the resistances are connected in series, parallel and series parallel. So first one will be of series connection. Series connection is nothing but the end of the first resistor will be connected to the end of the second resistor. So it is denoted like this. The first end of the first resistor will be connected to the first end of the second resistor. So this end will be connected here, and the end of the second resistor will be connected to the starting end of the third resistor. In this type, n number of resistors will be connected. So which will be denoted with R1, R2, R3 and Rn. So how to calculate the resistance when these resistors are connected in series? So by using this formula, which is nothing but R equivalent is equals to R1 plus R2 plus R3 and so on till Rn. So by using this formula, we need to calculate the resistance when they are connected in series. We have to remember the first point while calculating in series connection is, in series connection, the current will be same across all the resistances. If here the voltage source is connected, so this is positive terminal and this will be negative. When the current is flowing from here, all the resistors will carry the same current. In the series connection, the current will be same through all the resistors. Current is same. So coming to the voltage, in series connection, the voltage will be different across each element of the resistance. So we need to remember these 2 points. One is current will be constant and voltage will vary across each resistor. So these 2 points we need to remember while calculating for the series connection, and the formula used to calculate when the resistors are connected in series is R equivalent is equals to R1 plus R2 plus R3 and so on till Rn resistance. So next one, coming to the parallel connection. In the series connection, we know that the current will be constant across each resistance, but in the parallel connection, the current will divide. So this will be the circuit diagram for the parallel connection. See, all the first ends will be connected to a single line and all the second lines will be connected to a single line. So in this way, the parallel connection is denoted R1, R2, R3 and till Rn. So here it will be the voltage. So if the current is flowing in this direction, again it is dividing here, which is taken as I1, I2, I3 and IN. So if the current is dividing in the circuit, then the connection is said to be in parallel. And the voltage across the parallel connection will be constant. Here we need to remember 2 points, which is one is of current will divide. Voltage will be constant. So in the series connection, the current will be constant and voltage will divide. In the parallel connection, current will divide and the voltage will be constant. So we need to, if we need to calculate the equivalent resistance of parallel network, we need to use the formula 1 by R equivalent is equals to 1 by R1 plus 1 by R2 plus 1 by R3 and so on till Rn resistances. If the two resistances are connected in parallel, we need to use the formula which is taken as R1 and R2. So we need to use this formula which is R equivalent is equals to R1 into R2 by R1 plus R2. So this is the formula which we have to use while calculating the parallel connection. And next, moving to the series parallel combination. So while calculating the combination of series parallel, we have to remember few points which are taken as: first is to identify the series and parallel groups in a circuit, and second one will be to reduce the first parallel group connections, and third one will be add the resistances which are in series and repeat until you get a single equivalent resistance. So these 4 steps you need to follow while calculating the resistances when they are connected in series and parallel combination. So example circuit for series and parallel connection is taken as so this is the example circuit for the series parallel combination. By following these steps, first we need to identify the series parallel groups. Here these 2 resistors are connected in parallel and these 2 resistors are connected in series. So first what we have to do, we have to identify the series parallel groups and then we need to calculate the parallel groups in the first. So here are the parallel groups resistors R3 and R4. If there are 2 resistors connected in parallel, we need to use formula R is equals to, or we'll denote it as R5. R5 will be equals to R3 into R4 by R3 plus R4. So we'll get a resistance which is named as R5 and we have to reduce this circuit again. This will be reduced as, here the 3 resistors will be connected in series which is R1, R2 and which will be R5. Now if we see, the resistance across points A and B will be connected in series which will be calculated as R equivalent is equals to R1 plus R2 plus R5. Then we'll get a value which is taken as R6. So the R equivalent will be denoted with R6. So in this way, first we have to identify the parallel circuits and then we have to add the resistances which we have connected in series and we have to repeat these steps until we get a equivalent resistance. So here is the example problem so that we can get an idea how to calculate when the resistors are connected in series, parallel and series parallel combination. So here is the first example on when the resistors are connected in series. Here are the 3 resistors which are connected in series. So how to know if the resistors are connected in series or not? If here is 10 volt supply given and the current I is flowing in this direction. So here the current is same across all the resistors. If the current is same across all the resistors, then the connection should be taken as series connection. So to calculate the equivalent resistance in series circuit, we have to take it as R1 plus R2 plus R3 and so on till Rn. So here are only 3 resistors which are connected in series. First resistance value is taken as 5 ohms. Second will be 3 ohms. Third one will be of 2 ohms. So now we have to take 5 plus 3 plus 2. The value of this will be 10 ohms. The R equivalent will be taken as 10 ohms. So if we want to calculate the current, so normally we need to use a formula which is from the Ohm's law, which is equals to V into IR. So here we are having the voltage value and we got the resistance value. From that, can we calculate I? Yes, I is equals to V by R. So which is 10 by 10, which will be equal to 1 ampere. So the current across this circuit will be taken as 1 ampere. So moving to the next example, we have seen how to calculate the resistors when the resistors are connected in series. Now we are going to see how to calculate the resistances when they are connected in parallel. So how we have to know that the connection is in parallel or series. When the current is dividing in the circuit, then the connection is said to be in parallel. If the current is same across the circuit, then it is said to be in series. So if the current I is flowing in this circuit and here it is dividing as I1, I2, I3, and then this circuit is said to be in parallel. So how to calculate the resistances when they are connected in parallel? So the normal formula for this is 1 by R equivalent is equals to 1 by R1 plus 1 by R2 plus 1 by R3 and so on till Rn. 1 by Rn. So first we have to calculate by considering two resistances. So from opposite to the source side, we have to consider the resistances. This is the source side and this will be the opposite side. Opposite side, these two resistances are connected in parallel. So first we have to reduce these two resistances, which is taken as R equivalent is equals to 6 into 3 by 6 plus 3. So this will be 18 divided by 9, which will be the value of 2 ohms. So after calculating these two resistances, we are getting the value of 2 ohms. Again, we have to reduce this circuit as. So here will be the supply. So we have not calculated this resistance. And after reducing these two resistors, we'll get a single resistance which will be in parallel with the previous resistor. R1 will be taken as 2 ohms and here, so we can consider this as R4 which will be of 2 ohms. So now these two resistors are also in parallel. So we have to reduce these two resistors and then we can calculate it as R5 is equals to 2 into 2 by 2 plus 2, which is of 4 by 4, which will be equal to 1 ohm. So the value of R equivalent will be taken as 1 ohm. The single resistance with source will be taken as a resistance in will be of R equivalent will be taken as 1 ohm. In this way, we need to calculate the resistance when they are connected in parallel. So we have to remember that when the current is dividing in the circuit, then the circuit is said to be in parallel. If the current is same across the circuit, then it is said to be in series. So in the series parallel combination, so here is the series parallel combination. In the series parallel combination, the current will also divide and the voltage will also divide depending upon the circuit. So while calculating the series parallel combination, first we have to see the combinations of series and parallel. So here is one resistance connected in series with these two resistances. So these two resistances are in parallel. So first we have to solve the combination of parallel. So first we have to solve this combination, which is R equals to 6 into 12 by 6 plus 12, which is 72 by 18. We have to take the resistance in the terms of decimal value. So the resistance value will be of 4 ohm. Then we have to reduce this circuit. It will be reduced with two resistors will be connected in series. The value of the first resistor will be taken as 4 ohms. And the value of the second resistance will be of 8 ohms. So now we need to calculate the equivalent resistance across these two resistances. Now these two resistances are connected in series because there is no current division here. The same current is flowing through it. Then it should be calculated with 4 plus 8, which is equals to 12 ohms. Final R equivalent value will be taken as 12 ohms. So in this way we have to calculate the resistance when they are connected in series, parallel and series parallel. Now we have seen how to calculate the resistances when they are connected in series parallel and series parallel. Now how to calculate the inductance or capacitances when they are connected in series and parallel we have to know. So in this way we'll be calculating the resistances when they are connected in series, parallel, and I have already mentioned how to calculate when they are calculated with the combination of series and parallel. So we have to know how to calculate the inductances and capacitances are connected in series and parallel. So while coming to the inductors, how to calculate when they are connected in series means the same way how we have calculated for the resistances, and the same way we have to calculate for inductances also. When the inductors are connected in series, we have to add all the sum of inductances as same as resistance. So here is the formula to calculate the inductances, which will be L equivalent is equals to L1 plus L2 plus L3 as same as how we have calculated for the resistances. In the same way we need to calculate for inductance also. In the same way, for the parallel circuits also, we have to multiply. Like if they are connected in parallel, we have to use the formula 1 by L equivalent is equals to 1 by L1 plus L2 plus L3. How we have calculated for the resistances, in the same way we have to calculate for inductance also. So coming to the capacitance, it will be different for resistors, inductors and capacitors. So while considering capacitors when they are connected in series, here we need to multiply. There we have added all the sum of sum of resistances and inductances. Here we need to multiply. See, this is a formula how to calculate the capacitances when they are connected in series. So the equation will be of 1 by C equivalent is equals to 1 by C1 plus C2 plus C3. So in this way we have to calculate when the capacitances are connected in series. The same thing when they are connected in parallel, we have to add all the sum of resistances. In the coming to the resistors and inductors, there we have multiplied all the inductors and resistors. Here we need to add all the. So while coming to the capacitors, when they are connected in parallel, we have to add. This is the formula which we need to use while adding all these capacitors when they are connected in parallel, which is C equivalent is equals to C1 plus C2 plus C3. So we'll see one example problem by using capacitors and inductors. So here is the example problem when the capacitors are connected in combination of series and parallel. So here is the question: calculate the equivalent capacitance of a combination shown in figure below across X and Y. These are the X and Y terminals. Across this terminal, we need to calculate C equivalent. So first, when there is a combination of series and parallel, first we have to see how many combinations are there in this circuit. So here is first two series capacitors connected in series, and these two capacitors will be in parallel with this, and after reducing this circuit, this will be in series with this capacitance. So after solving these three steps, we'll get a C equivalent. So first we'll reduce these two series circuits. When the capacitors are connected in series, we have to use the formula 1 by C is equals to 1 by C1 plus 1 by C2. So here it is taken as 2 into 2 by 2 into 1 by 2 into 1 by C1 plus 1 by C2 plus 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 1 by C2 plus 1 by C1 plus 1 by C2 plus 1 by C1 plus 1 by C2 plus 1 by C1 plus 1 by C2 plus 1 by C2 plus 1 by C1 plus 1 by C2 plus 1 by C1 plus 1 by C2 plus 1 by C2 plus 1 by C2 plus 1 by C1 plus 1 by C2 plus 1 by C1 plus 1 by C2 plus 1 by C2 plus 1 by C2 plus 1 by C1 plus 1 by C2 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 2 plus 2, which is 4 by 4. The value of the capacitance will be of 1 microfarad. So after reducing this two series capacitor, the circuit will be redrawn as so this will be the circuit after redrawing. So here it will be 1 microfarad and the terminals across it will be X and Y. So after that we have to reduce these two parallel resistors. If the resistors are connected in parallel, we have to add these two resistances which will be 2 plus 1 is equals to 3 microfarad. Again we have to redraw the circuit. Then the two capacitance will be connected in series across two terminals X and Y. One will be with of 3 microfarad and another one will be 1 microfarad. So when these two capacitors are connected in series, again we have to multiply the two resistances, which is of 3 into 1 by 3 plus 1. So the value will be of 3 by 4. Total equivalent capacitance will be taken as 0.75 microfarad. So the capacitance across terminals X and Y will be taken as 0.75 microfarad. So in this way we have to reduce the circuit and we need to calculate the inductance or capacitance or resistance across each circuit when they are connected in parallel or series or combination of series and parallel. So we'll see one more example on inductances when they are connected in series parallel combination. So here is the series parallel combination of inductors. So first we need to identify how many combinations are there in this circuit. So first, considering from the opposite side of the source, these two inductances will be connected in series. So how to calculate the inductances when they are connected in series and parallel? It should be calculated in the same way how we have calculated for the resistances. So first, if they are connected in series combination, we have to add the inductances, and if they are connected in parallel we have to multiply. So first combination is of series combination. So we have to reduce these two circuits. So till here L7 inductances are connected. I'll take it as L8. So I'll write it here. 40 plus 100. The value of inductance will be 140 millihenry. So again we have to redraw the circuit after reducing these two inductances, which will be redrawn as 3 inductances. Which is of EAP, and the value of reduced inductance, which is of L8, will be taken as 140 millihenry, and L6, sorry, so here will be, okay, sorry. So after reducing these two series circuits, we'll get a value of L8 inductance. The value will be of 140 millihenry. And this will be 50 as usual, 20, 30, 20, 40. Now again we have to see the combination of series and parallel networks. So again coming to the opposite side of the source, these two inductance will be connected in parallel, which should be calculated by using the formula 50 into 140 by 50 plus 140. The value of the inductance will be of 36.842 millihenry. So if we calculate by using this formula, which is of L1 into L2 by L1 plus L2, we'll get this like these two inductances will be connected in parallel, which is of 50 and 140. So 50 into 140 by 50 plus 140, the value of the inductance which will be taken as L9 will be of 36.842 millihenry. Again, we have to redraw the circuit after reducing these inductances. The circuit will be redrawn as so the reduced inductance will be L9 is equals to 36.842 millihenry. This 20 millihenry will be as it is, 30 will be as it is, 40 will be taken as it is, and 20 will be as it is. So after reducing this circuit, again we have to see the combination of series and parallel. So these two inductors are connected in series. Again we have to reduce this circuit. So to reduce these two inductances when they are connected in series, we have to add these two inductances which are of 20 plus 36.84 and which will be taken as L10. The inductance value will be taken as L10, which is denoted with L10. So 20 plus 36.84 will be around 56.84 millihenry. So again we have to redraw this circuit after reducing these two series inductances. This will be redrawn as, so here I'll be drawing the circuit. This is A, B. The value which we got is of L10, which will be of 56.842 millihenry, and the value of this inductance will be of 30 millihenry. This will be 20 and this will be 40. So again we have to see the combinations now. Here these two inductances are connected in parallel and we have to simplify the circuit again. So if these two inductances are connected in parallel, we have to reduce the circuit. We have to use the equation which is of L1 into L2 by L1 plus L2. So it is considered as L1 or L2, or if it is considered as, this will be of L1, L2, L3. So the formula will be L3 into L10 by L3 plus L10. So the value of L3 is 30 into 56.842 by 30 plus 56.842. Again it will be taken as 11. The value of 11 will be around 19.636 millihenry. So after calculating these two inductances when they are connected in parallel, again we have to redraw the circuit. So after reducing these two things, we'll get a circuit as inductor, terminals across AB. It will be L2 will be taken as 40, L1 is 20, and L11 will be of 19.636. So again we have to see the combinations of series and parallel. So L2 and L11 are in series. If they are connected in series, we need to add the two inductances which will be taken as L12 is equals to L2 plus L11. So if we add these two inductances, we'll get 40 plus 19.636. So the value of L12 will be 59.636 millihenry. So after calculating these two resistances, again we have to redraw the circuit. So these two will be in series or parallel. These two inductances will be in parallel with each. Because the current is dividing here and here, so these two will be connected in parallel. Again we have to draw the inductance circuit, which will be reduced into L12 is equals to 59.636 millihenry, and actual L1 value will be of 20 millihenry, which is taken as A and B. Now if these two inductances are connected in parallel, then we have to calculate these two inductances by using the formula L1 into L12 by L1 plus L12. So it will be taken as 20 into 59.636 by 20 plus 59.636. So the value of L equivalent will be 14.977 millihenry. So the final circuit will be drawn as the terminals A and B. The inductance across the terminals A and B will be taken as 14.977. This is the value of L equivalent. In this way, we have to calculate inductances or capacitances or resistances when they are connected in series parallel and series parallel combination. So in the next session, we'll be discussing more complex problems on the calculations of equivalent resistances. That's it for today's session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.